Alright, I'm going to go through this a little quickly too because we can graph these in Desmos. I've put in week 6 and week 7 a little video on how to graph these in Desmos. So if at the bottom left hand side there's a little keyboard, and I go to functions under calculus, but this video that I posted shows a keyboard shortcut that makes it even easier. So instead of just remaking a video that said the same thing, I posted that one in the lecture notes section. So to graph logarithmic functions, you can rewrite it in the form in its exponential form. So this 2 will bump up this y, so 2 to the y equals x. And then we'll plot the graph of the function, and it'll be easier to start with values of y than get x. So if I have y equals -2, then it becomes 2 to the -2, which is 1/4. You just have to remember that's x, so you got to write that in the right place. Then you get your points, draw a smooth curve, and Desmos will do that for you even quicker than that. Oh. Make sure I don't have any more notes to myself in the future, or from the past. Notes from the past to the future. Excuse me. Alright, so let's graph this one. We're only going to go through the pane once. We're going to write this as 1/3 to the y equals x. So I'm going to pick the point y equals 0, 1, and -1, and that will give me 1/3 to the 0 power, which is 1. Remember, that's my x. 1, 0. And then it gives me 1/3 to the 1, which is 1/3. So that is 1/3, 1. And then 1/3 to the -1 gives me 3. So that is my x. So I have 3, -1. And then I plot these. And so that is 0, 1, 1/3, 1. It's really hard to see on there. And then 3, -1. And then round out my curve. This is a generic form. This isn't this problem. This is the point 1/a, comma -1, 1, 0, and a1. Alright, so the domain of an exponential function, recall, is the domain is all real numbers and the range is 0 to infinity. And because they are inverses, we flip them, so the range now of a log function is 0 to infinity, and the domain is all real numbers. And so we cannot take the log of a negative number. So we have to make sure that we don't have any exceptions, or we have to define our domain. So here I have log base 4 2x minus 3, and I have to make sure that whatever comes in these parentheses is positive. So you have to make sure that 2x minus 3 is greater than 0, or x is greater than 1.5. So the domain of this function is 1.5 comma infinity, or x is greater than 1.5. So to find the domain, you're going to set up an inequality showing the argument greater than 0, solve for x, and then write an interval notation. So this is x plus 3 has to be greater than 0, or x has to be greater than -3, so that's -3 to infinity. And here 5 minus 2x must be greater than 0. 5 is greater than 2x, or 5 halves is greater than x, and of course if we rewrite it, since the mouth is open to 5/2, it has to be open to the 5/2, so we rewrite it, and that is 5/2, comma, infinity. Alright, so it goes through graphing, and it shows like to the x it's here. This is log base 2 of x, okay, and these are reflections about the line y equal x, and we would expect that from inverses. So let's talk about the characteristics of the graph apparent function. Log base b of x, it's a one-to-one function, has a vertical asymptote of x equals 0, domain is 0 to infinity, range is all real numbers. X-intercept at 1, 0, and it has a key point at b1. Y-intercept is none, increasing if b is greater than 1 and decreasing if b is a fraction. So this is the graph if b is greater than 1, and this is the graph is if b is a fraction between 0 and 1. And then this shows how changing the base can affect the graphs. So this is log base 2, this is natural log of e, and this is log base 10. So if you want to do this by hand, which you should go to Desmos and do it there, draw and label and your vertical asymptote at x equal to 0. Plot the x-intercept, plot the key point at b comma 1, draw a smooth curve to the points and state the domain and range and the vertical asymptote. So here's log base 5 of x. Since b equal 5 is greater than 1, we know the function is increasing. The left tail of the graph will approach the vertical asymptote x equal to 0, and the right tail will increase slowly without bound. The x-intercept is 1, 0. And the key point, because it's got a 5 here, is 5, 1 on the graph, and then you will label and draw your smooth curve, and domain is 0 to infinity, and the range is all real numbers, and your vertical asymptote is x equal to 0. So these are shifts left and right, so you'd have a plus c that would move it to the left, and a minus c would move it to the right. And this tells you domain and range like we're used to. If we have a horizontal shift, then okay, we're going to identify the horizontal shift here. So if I have the log base 3 of x minus 2, we take the opposite sign. So this is a minus. We know this would go to the right, or right 2 units. So this is the parent function, and this is the shift. Now, vertical shift, you would add or subtract outside of the function. A positive goes up, a negative goes down, just like we've had before. Graphing a vertical shift of a parent function log base x. So you would take this function, and then you would move all of them down, all the y's down 2 units. So this is log base 3x, and this is log base 3 minus 2, which is a lot more work to do by hand than if you go to Desmos. And then you have stretches and compressions. So if you have a number multiplied outside the log, that's going to give you a stretch, and if you have a fraction, it's going to give you a compression. This is doing it by hand. We're not doing it by hand, but this is log base 4 of x, and this is 2 times log base 4 of x, so you can see the difference here. And then, so this says sketch this graph of 5 times log x plus 2, state the domain, range, and asymptote. So the vertical asymptote will be shifted to -2, which is right here. The x-intercept will be -1, 0. The domain will be -2, 0. The 2 points help give shape of the graph. 1, 0, and 8, 5. We choose x equal 8 as x-coordinate of 1 point because when x equals 8, x plus 2 equals 10, and that's a base of a common logarithm. But I would just throw it into Desmos. So this is a reflection about the x-axis if you have a negative on the outside, and if you have a negative on the inside of the operator, it's about the y-axis. So these go through steps by doing it by hand. If you want to meet on Teams and go through all this by hand, we can, but we don't need to. We have a much better graphing utility. And then, so this is log of negative x and log of x, so you can see the reflection. It shows how to do it in a calculator. So now this is approximating the solution of a logarithmic equation. So anytime we have two things that equal each other, that we find where they intersect, that's where they're both true. So if I take and graph this one as my first equation, this is my second equation, on Desmos I can see where they intersect, and that will be the answer. So I put it in Desmos here. So in black is the y equals 4 natural log x plus 1. And then in the red is y equals negative 2 natural log x minus 1. And then I clicked, it already has like a little dot, I clicked on it and I labeled it, so it's the 1.33853, comma 2.16629. So I'm able to type in on Desmos, I said they are equal at x equals 1.33. And that is approximately 1 1/3. And then this is a summary of what we talked about. And like I said, Desmos, do it in Desmos. This was a lot of heartburn for me in school. It shouldn't be. You should kind of know what you're looking at, but there's nothing wrong with doing it, working hard and smart by putting it in Desmos. So if you want to see more examples, as always, these links are live in your lecture note PDF. And if you have any questions, you can come by office hours or send me a Canvas message, and I'm happy to talk to you.